So hello and welcome to what is hopefully the last lecture of the course. So in this lecture today, we are going to be looking at magnetic dipole radiation, which will be very similar to what we did for the electric dipole radiation last time around. So what we have here is we have, as you can see in the figure below, you have a wire loop of radius b around which we will drive an alternating current I, and that I of t is going to be of the form I naught cosine omega t. Now this is a model for an oscillating magnetic dipole where m, the magnet m of t, is given as pi b squared I of t, and this is in the z direction. And so the point essentially, so we are going to call this just m naught into cosine omega t z cap. Very good. And so that's that, where m naught, of course, is given by pi b squared I naught. And this is the maximum value of the magnetic dipole moment. Okay, the loop is uncharged, so let's loop is uncharged, so hence v is equal to 0. The retarded vector potential, on the other hand, is given by a RT. This is nothing but mu naught by 4 pi integral of I naught cosine omega t minus r over c by r d l prime. Okay. So now let's look back at the figure, and what we want to say is that for a point R that is directly above the x-axis, for that A has to be in the y direction, since the x components from symmetrically placed points on either side of the x-axis is going to be equal to 0. Okay, so this amounts to an expression of A, which is just given by mu naught I naught b by 4 pi integral of 0 to 2 pi cosine of omega t minus r over c by r cosine of phi primed d phi primed, where phi primed, as you can see in the figure, is just the way this has been written out. So phi prime, cosine of phi prime, you get that because that sort of picks out the y component of the line element dl prime. Okay. Now again, r is nothing but r squared plus b squared minus twice br cosine of psi, of course square root of this, where the psi is again given in the figure is the angle between these two vectors r and b. Okay. Now what? Now let's try to write down r and b in terms of, so let's write down r and b. So r is r sine theta x cap plus r cos theta z cap. So this is in the xz plane. B on the other hand is in the xy plane. So this is b cos phi primed x cap plus b sine phi primed y cap. So now of course br cos phi, cos psi actually, so this guy that we have written out here is of course just twice b dot r, right? And twice b dot r in this language is just given by, if you just do this product, this is just twice br sine theta cos phi primed. So if you put these together, so this so then what you have is an expression for r, which is r squared plus b squared minus twice br sine theta cos phi primed, this whole to the half. Now we are going to do like we have done our series of approximations. Okay. So approximation 1, like in the previous case, is that we want a perfect dipole, so we actually want the loop to be very small. So b has to be much less than r. So this in turn just means doing exactly the things that we did last time. This means that 1 over r is just 1 over r, 1 plus b over r sine theta cos phi primed. And similarly, so what we have is cosine of omega t minus r over c is given by, so this is exactly again the same approximations as we used last time around. I'm not going to repeat that. So t minus r over c into cos of omega b by c sine theta cos phi primed minus sine of omega t minus r over c sine of omega b by c sine theta cos phi primed. So that was, if you remember, our first approximation. Then we come to our second approximation, approximation 2. That is b is much less than c by omega. Again, as you know, what we will so then again the cos theta will be approximated by 1 and the sine theta will be approximated by theta. So in this case you just replace the things like we've done last time around, and doing this what you get is an expression of a. So a rt, after doing these approximations, which I urge you to try and follow as we did last time around, this is y cap. I hope I've written down the y cap in the previous one. and I have not. This is y cap. So you have two terms now, 0 to 2 pi. First integral is cos of omega t minus r over c plus b sine theta cos phi times 1 over r cos of omega t minus r over c minus omega over c sine of omega t minus r over c. This whole multiplied by, so I don't have space, so let me move this around a little bit. Shouldn't have moved by 0. Okay, so this is times cos phi primed d phi primed. Now notice that the first term actually integrates to 0 because 0 to 2 pi of cos phi primed d phi primed is equal to 0. And the second term has a cos squared in it, so 2 pi cos squared phi primed d phi primed is actually equal to pi. So let's put these things in and notice that A in general points in the phi direction. So then what we get is that the vector potential r theta phi t is given by mu naught m naught by 4 pi to sine theta over r into 1 over r cos omega t minus r over c plus omega over c sine of omega t minus r over c. And again, I'm out of space, so this is in the phi direction, so let me put a phi cap here. Okay, now you'd remember a third approximation that is going to the radiation zone, approximation 3. Okay, so firstly, one thing to check off the list is when we look at the static limit, that is omega equal to 0, this term just drops. So this whole this becomes equal to 0, and this term, this factor becomes equal to 1, and so what you have is just a is mu naught m naught phi cap by 4 pi into sine theta by r squared. This is the usual static answer that you have. So let's just so this is the static case. So so that gives you the right answer. Okay, so this is the correct answer. Okay, for the moment, let's forget that I wrote these things down, and so oops, sorry. So yeah, so now so the as I said, the static answer is fine. So we want to, but we do not want to look at this. We want to look at the radiation zone where r is much greater than c over omega. And when we do this, what we get is we get an expression for A, which is A r theta t is equal to minus mu naught m naught phi cap. So let's not write the phi cap here. Omega by 4 pi c sine theta over r into sine of I've made a sign mistake here. This is a minus. Very good. So sine of omega t minus r over c phi cap. Okay. This is the expression that we want. And let me actually box up this equation for us. Okay. Very good. So this is the expression that we want. Okay. And so then what we can do is we can write down the electric fields and the magnetic fields, and so there is so the expression for the electric field is just minus del A del T. So this is mu naught m naught omega squared by 4 pi c sine theta over r cos of omega t minus r over c. This is phi cap. B is curl of A. This is minus mu naught m naught omega squared over 4 pi c squared sine theta over r cos of omega t minus r over c. This is theta cap. And we are interested in so we are interested in what the Poynting vector looks like. So r, so S of RT is equal to 1 over mu naught times E cross B. The expression for this is just simply mu naught over C m naught omega squared by 4 pi c sine theta over r cos of omega t minus r over c, the whole squared, and r cap. And the intensity is given by the average of this is mu naught m naught squared omega to the 4 by 32 pi squared c cube sine squared theta by r squared r cap. And the total power radiated is P, which is equal to mu naught m naught squared omega to the 4 by 12 pi c to the c cube. Now notice that again, so the power radiated actually goes less omega to the 4. But there's one very important distinction between electric and magnetic dipole radiation. For configurations which have more or less comparable dimensions, what happens is that the power radiated electrically is enormously greater than that radiated magnetically. To see this, let's just quickly do an estimation. So P magnetic by P electric is equal to m naught by P squared C whole squared. So you'd of course, so m naught is, remember, this is pi b squared I naught, and p naught is q naught d. And I naught is essentially, if you look at it, is pi b squared q naught omega. So let's put d is equal to pi b for comparison. So then P magnetic by P electric is going to be given by omega b over c whole squared. Now remember, look at what our approximation to was. Approximation 2 is given here. Approximation 2 is that b is much less than c omega, right? This is precisely the stuff that you have here. This was supposed to be small, and now we have squared it. So this is much less than 1. So as you can see, I mean, ordinarily one should expect that the dipole radiation would, dominate. The electric dipole radiation will dominate over the magnetic dipole radiation. Only when you have something where the electric dipole thing is equal to 0, then only the magnetic dipole radiation will reveal itself, if you will. Okay, so that's about the magnetic dipole radiation. What we will quickly do now is we will look at the radiation from an arbitrary source. Okay, so let's do this. Radiation from an arbitrary since you could have of course started off with this, but instead of doing that, we try to run through a few more things. So let these be the axes, x, y, and z, and actually let's put this okay, so let me just try and draw something. So this is an arbitrary charge distribution. And there's this box here. And you have this point P. This is the point P. This is R primed. This is R. This is another R. That's Z. That's Y. That's X. And you have a charge distribution here. This is theta primed. Let's say that you have a charge distribution in this region, and we want to find out what is going to happen. So we have right now looked at the radiation produced from an oscillating electric dipole and an oscillating magnetic dipole. Now what we want to do is we want to apply the same sort of things to configuration of charge and current that is arbitrary, except for the fact that it's localized within a certain finite volume near the origin, as we have in the figure here. So the retarded potential that you have in this case is V of RT. Let's move this down a bit, actually. Yeah, so V of RT is given as given by 1 over 4 pi epsilon naught integral of rho of r primed t minus r over c by r d tau primed, where r in a usual way is given by r squared plus r primed squared minus twice r dot r primed, and so to the half, right? Now what are we going to do? We are going to make the approximations that we were making earlier. So rather, let's say approximation 1. This is r prime is much less than r. Okay, so the field point r is very far away to the dimensions of the source. Okay, so now what happens? Since the math is a little more involved, I want you to pay a little closer attention. So let's use black actually. So r is approximately equal to, so we're going to drop the r prime square bit first. So r into 1 minus r dot r primed by r squared. Notice that we have also expanded this, so the factor of half goes down because we have expanded the 1 minus x to the n and brought down n. N here is equal to half. That takes care of the 2. So this essentially means that 1 over r is approximately equal to 1 over r times 1 plus now r dot r primed by r squared. Okay, very good. Now rho of r primed t minus r over c in that case is approximated by rho of r primed minus r over c plus r cap dot r primed over c. Okay, very good. So that's straightforward. Now what you want to do is we want to expand this. So expand this guy. So okay, so we are going to expand in a Taylor series. In t about the retarded time. Retarded time is t naught is equal to t minus r over c. Okay, so let's do that. So let me also just quickly remind you that Taylor series, if you have f of x and you are expanding this f of x, around x equal to a, then this becomes f of a plus f primed of x minus a. So this is at x equal to a, that's plus 1 over 2 factorial to f double primed of x at x equal to a, x minus a the whole squared, plus dot 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 dot. That's your expansion around x equal to a. Okay, so in this case, what are we doing? We are expanding rho of r primed t minus r over c around rho equal to 0. So the first one, of course, is r primed t naught plus the second term is going to be the derivative of rho with respect to this. So that's rho dot r primed r prime t naught, and x minus a in this case is r dot r cap dot r vector by c, plus the other terms in the expansion are like half rho double dot r over c squared plus dot dot dot. Okay, now what we will do is we will use approximation 2, and approximation 2 is going to be r primed is much less than c by rho double dot by rho dot, and things like rho triple dot by rho dot to the half, and so on. So this, what happens is for an oscillating system like the ones we have seen before, each of these ratios is over just c over omega, and we recover the old approximation. But in a sense, what is happening out here in the in this particular more general case is that we just need to keep first order terms. So operationally, this just means keep terms only. So keep rather only keep terms first order in R primed. Okay, so that is what this is operationally. So if we just do this, and if we plug this back in, so this is what we have. So V of RT in this case is just going to be given by 1 over 4 pi epsilon naught integral of, if you remember, rho r primed t minus r over c over r d tau primed. So now this becomes 1 over 4 pi epsilon naught. So the integral, so what we have is we have this term as we have written up there. So that's rho of r primed t naught plus rho dot r primed t naught into r cap dot r primed by c. That's one term. And the second term just comes from the 1 over r. So that is the term which is 1 plus r dot r primed by r squared divided by r. Okay, so these are the two terms that you have. So taken together, now this just simply means that this is going to be equal to 1 over 4 pi epsilon naught integral. So of course there is an integral d tau primed rho of r primed t naught d tau primed. Let's put an r outside and put this bracket here, plus r dot integral of r primed rho primed t naught d tau, plus there's a third term which is r primed over c d dt of integral r dots here rho, there's a dot here, r primed t naught d tau. Now what is this expression? This expression simply is the following. This expression, so this is approximate, okay? These are all approximate. So v of rt is approximately equal to 1 over 4 pi epsilon naught. So the first term is just q over r. So q is the total charge at time t naught. Okay, this is independent of time because charge is actually conserved. The second and the third integrals represent the electric dipole moment at a time t naught. So this is very simply plus r dot p at t naught by r squared plus r dot p dot at t naught by r into c. Okay, so that's that. Now this is the expression for v. So what is the expression for a? A is simply rt is mu naught over 4 pi integral of j r primed t minus r over c by r d tau primed. So so the first order in r primed, it just suffices to replace this curly r by r, and so this essentially becomes mu naught by 4 pi integral of j. You can replace this by r, and this is j of r primed t naught d tau primed, which is nothing but mu naught over 4 pi r into p dot of t naught. Okay. Now we come to our final approximation. Approximation 3 is discard 1 over r squared terms in E and B. So you remember, if there were 1 over r squared terms in E and B, what would happen is those parts of the Poynting vector would follow faster than 1 over r squared, and hence when you try to compute the power, that particular thing, when you take the limit of r goes to infinity after the integral, that'll just go away. So we need to drop terms which are 1 over r squared in E and B. So what happens is, of course, for example, if you have, the Coulomb field that comes from the first term in V, that of course does not contribute to the electromagnetic radiation, and the only terms which will actually arise from it are the terms where we differentiate the argument T naught. So remember that the divergence of T naught is just 1 over C times the divergence, the gradient, phi, which is minus 1 over C times r cap. All right, and then hence what we have is the gradient of V is approximately equal to the gradient of this last term. It's 1 over 4 pi epsilon naught r dot p naught dot t naught, so not p naught, sorry, p t naught by rc, which is given by 1 over 4 pi epsilon naught r p double dot t naught by rc into the gradient of t naught. Therefore, gradient of V is minus 1 over 4 pi epsilon naught c squared r cap dot p double dot t naught by r in the r cap direction. So that's the electric field. So that's that. And what else do we have? So that's one part of E. The other part of E, you can just compute dA dt, and that comes out to be approximately equal to mu naught by 4 pi p double dot t naught by r. So E is given by mu naught by 4 pi of r cap dot p double dot r cap minus p double dot which can be more compactly written as mu naught by 4 pi r cap cross p double dot. So this is the expression for E, where this p double dot is evaluated at t naught equals to t minus rc. B is also approximated by something like minus mu naught by 4 pi c r cap cross p double dot. So you can find out what S is. S of RT in the usual way, 1 over mu naught E cross B, and you can find out the formula for that. What I will do is I will write down the final expression for P radiated at T naught. So this is equal to mu naught by 6 pi c p double dot at T naught, the whole squared. Okay. All right. So what we have been looking at in this particular section, particular last bit actually, it amounts to a sort of multiple expansion of the retarded potentials carried out in the lowest order in R prime, and it shows us that this actually amounts to the I mean, let's quickly, so yeah, this would actually show us that this amounts to the dipole term. So let's just very quickly see this. So if you have P of t is equal to P naught cosine omega t, then P double dot of t is minus omega squared P naught cosine omega t, and we are going to recover all the previous results. Of the so what we did for the electric of the electric dipole. Now, so I would just want to end with this. So this multiple expansion carried out to lowest order in R primed is capable of producing electromagnetic radiation. This is what we have seen as a dipole term. So if it were to happen that this particular dipole term were to vanish, then one must look at the next term, that is the next order so if you wish, the second order in R primed. This can be actually separated into two parts. One of them is related to the magnetic dipole moment of the source. The other is actually related to the electrical quadrupole moment. Then if somehow these two were also to vanish, then one will have to look at the R prime cube term, this would yield the magnetic quadrupole and the electric octopole and so on and so forth. So it gets organized in this way, okay? So that's what we have learned here so far. So what we have learned is that, when we are looking at, just to get back to the main thing of the whole section, if you wish, what we wanted to say that we had earlier seen that Maxwell's equations will allow for plane waves. So that was light. And we wanted to ask how you can generate waves from a collection of electric charges. So we see that if we saw that a stationary electric charge produces a stationary electric field. If we boost this charge to move at a constant speed, this yields a stationary magnetic field. And finally, we have seen that if we go to a non-stationary situation, which actually corresponds to accelerating electric charges, we will see propagating electromagnetic waves. I am more or less done, but I have a lingering feeling that I should say a little bit more about accelerating point charges. So I'll spend about 15 minutes on this in a shorter video next time around, and that will for sure wrap up this course. So that's it from my side now. Hope this was not too heavy, and keep asking me more things so that I can clarify a few of the doubts that you might have. All right, so that's all from my side now. Thank you.